All right, taking a look at number 7. So number 7 from the exam number 4 from 2014. And we'll go to letter E, and it has a fill in the box. It has HgOAc2 with some H plus in there, and then water as a solvent, and the product is this ketone. And the question is, what is the starting material? All right, so first thing I'm going to do, I'm going to number all the carbons. 1, 2, 3, 4, 5, and 6. The other big thing to notice is here, there's only one product. So since there's only one product, you got to be a little careful here where the alkyne goes. Right? So you know this is a ketone. So if I took one step back, what's the starting material? What would this have came from?
Enol.
It could have came from an enol. Which enol?
You said there was only one?
It's only one product in E. Or you could even, if you can see it, go farther all the way back to the alkyne. Which enol did this come from? It could have came from either
So 1, 2.
this enol or
Is it that one?
this enol, right? 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Those are two possibilities. But they would have came from different alkynes, right? What two alkynes would these have came from? What alkyne would that one have came from? Where would the pi bond, where would the triple bond be at between which two carbons?
2, 3.
2 and 3, right? Because it'd be 1, 2, 3, 4, 5, 6. For this one, what alkyne would this have came from? An alkyne between which two carbons? 1 and 2. One, 2, 3, 4, 5, 6. Okay, so those are two possibilities. Which one's the right answer?
The one between 2 and 3.
Nope.
Okay.
If it's between, if you react Hg 2 plus and water and acid, you could get a ketone at carbon 2 for sure, but you could also get a ketone at carbon 3 because there's no preference. And we only show one product ketone. So it has to be this one, because for this one, with the terminal alkyne, we're only going to make the ketone at carbon 2 with this, right? Because this does a Markovnikov addition, makes a Markovnikov product, right? Where in this case, this like having the OH here is no different than having the OH on 2, right? It's an enol, but it could lead to two different ketones. So it has to be this one. If we only want one product, this has to be the alkyne starting material. So be careful with that one. All right, doing number 4D from exam 4 from 2014. So in that case, we have an oxygen here and a plus charge. So first thing we want to do is add in our lone pairs. So oxygen should have two lone pairs. So we want to know, the question is, determine the following compounds are aromatic, anti-aromatic, or non-aromatic. So to be aromatic, you had to have one of two, there's two qualifications. What are the two qualifications?
You have to be in a ring.
In a ring with what?
Uninterrupted process.
Ring with an uninterrupted pi system. That's right. Does this have an uninterrupted pi system? Yes, it does. Right. What's the hybridization state of a carbocation always? sp2. So that means it has a p orbital, right? Empty p orbital there. And this lone pairs, this oxygen are going to choose to be, this oxygen is going to choose to be sp2, so one of its lone pairs can be part of the pi system. And how many electrons do we want in the pi system to be aromatic? An odd number of pairs of essentially p orbital electrons. How many electrons do we have here? We have 1, 2, and then one of these is going in. So that's 3, right? Is that odd? Yep. Is this an uninterrupted system? Yep. So this is aromatic. Right, so you can have empty p orbitals and still be aromatic. That's not right. It has nothing to do. The rules for aromaticity have nothing to do, right, with empty or full. All it has to do is the odd number of pairs of p orbital electrons in an uninterrupted pi system. So you could have empty, you could have full. It doesn't matter, right? And so another thing is, since this hydrogen or this oxygen is choosing to be sp2 hybridized, one of the lone pairs is in a p orbital. Where's the other lone pair at? What molecular orbital is that in?
sp2.
It's in an sp2. Very good. Right, sp2 hybridized with a p orbital and 3 sp2s. So one of the lone pairs is part of this pi system. Okay, got a good question about what would some resonance structures of this look like? So they would look like so I can move this here, move those there. Alright, if I number everything, 2, 3, 5, 6. So now there's a pi bond between 1 and 2. Nothing changed over by these guys. One lone pair is used up. There's now a pi bond between these two. Right, number my carbons 1, 2, 3, 4, 5, 6. And you're missing one thing. What do I need to do?
Sure.
Where's the charge need to be? Oxygen. Balance my charge. So there's another resonance structure that's maybe a little easier to see as being aromatic. But it's aromatic. Yep.
And which one's more stable?
Which one do you think is more stable? What would be more stable? A or B? B, why? Everybody has a full octet in B.
Would
Yep.
you also say that like the oxygen can just spread out the charge better?
Nah. Octets. Octets.
So usually the more stable product is on the cluster is on a more electronegative atom.
No. More stable products than with the full octets.
Is that it?
Full octets. If you can have full octets, that's always going to be more stable.
So
Yep.
what if it was like when you, okay.
Take a look at number 6 from 2014, exam 4. It says you have something like this, and you react it with HBr, and the products are two things. And we called this one A. We also made B. Put a bromine there. Pi bond. So we number our carbons and oxygen, why not? 2, 3, 4, 5, 6, 7, and 8. 2, 3, 4, 5, 6, 7, and 8. 1, 2, 3, 6, 7, and 8. So the question is, how do we get A is hopefully easy to see, the easiest move for you guys, right? This pi bond attached between 5 and 6. Make a plus charge in the tertiary carbocation because that's also allylic, right? It would also be stabilized that way by pi bond resonance and have more hyperconjugation buddies. But if you make that intermediate, so if I draw that, and we can agree the first place there's going to be a plus charge is going to be here, right? We can also do a resonance form of that, right? So that we've made Br minus. So the easy one to see is this attacking there, and that gets us to A.
Oh, so
Right.
you just did residency?
Yep.
Okay.
Just
I
did
thought you
resonance, yep.
started from-
Nope, same star material, getting two different products, right?
That's
And
what I
the,
was like.
yep, and the biggest thing to think about, so we would have to, right, so if bromine is here, you knew carbon 5 had to be plus, had to be delta plus at some point.
Mhm.
And so you look at this one and say, well, if bromine is attached to carbon 3, then 3 has to be delta plus at some point. Right? It had to be. Right? Every bond you make, somebody has electrons, somebody wants them. So you can just do a resonance form. Right? Now the plus charge would be here. And which one of these two intermediates is more stable? A or B? Nope, it's B. Why is B more stable? Because this oxygen, well, technically this is more stable than all of them. Yeah, okay, fine, I'd give you that. If this is more stable than this, but the next resonance structure over, this is the best resonance structure, right? We can agree on that? So yes, this is probably better than this because this is tertiary allylic, this is secondary allylic, and this is full octets. And along the way, we had Br minus coming along the way, right, the whole time? So the last step, and that leads us to compound B, right? If we did a 1, 2, 3, 4, 5, 6, 7, and 8, right? Just because there's a plus charge on oxygen, where is it really delta plus at? It's really delta plus at carbon 3, right? And that's where bromine attacks.
Can you not add bromine on the compound 4?
You could add it on here.
Just right away.
But this is the best resonance structure, right? And that's why, right? Because one of the questions was, which will be the major product? And if you said this would be the major product with this resonance structure, it wouldn't make any sense, right? Because this is secondary allylic and this is tertiary allylic. So this is actually a more stable intermediate than this. So you actually have to show this most stable intermediate to rationalize why this is a major product. Do we see that? No? So you have three intermediates. You have three intermediates. You have intermediate A, intermediate B, and intermediate C. Right? Which intermediate is the most stable? C, because it has full octets. The most stable intermediate is probably going to lead to the most likely product. Right? So if you're going to say that B is the major product, or this question asks, predict which will be the major product and explain your reasoning. To explain your reasoning, you'd have to say, because it comes from the most stable intermediate, which has full octets right here. Showing this and saying it's the most stable intermediate wouldn't make any sense, right? Because this is secondary allylic, this is tertiary allylic. With these two resonance forms, you would predict this would be the most stable. So you need that third one to prove it to yourself. To see the full octet intermediate. And say, this is the most stable intermediate, this is the most stable product, which is also the major product, product B. Taking a look at a question about basicity. So you have two structures. You have aniline, which is on the left. And you have, this is called aniline. This is cyclohexane amine. And the question is, which is the stronger base? Which is the stronger base? So we're talking about bases. Are we talking about nucleophiles or electrophiles? What's a base? Is it electron rich or electron deficient? A base. Electron rich. So what part of this is basic? What part of these molecules is basic? The amine, but which part specifically? The lone pairs. So let's focus in on the lone pairs for both of these. So we want those lone pairs to be reactive, right? We want them to be reactive. They're going to be basic, they're going to be reactive. Which lone pair is more reactive? Would it be the one in A or the one in B? What's different about these?
Well, A's the benzene ring, that's more stable, so you.
A has the benzene ring, but what does that have to do with the lone pair?
It's a pi system, so like you could give away those electrons and balance out the charge with the pi.
I wouldn't balance out the charge, but I could spread the electrons out. So notice this lone pair is next to a pi system, right? So what could this lone pair do? It could have resonance structures where, right, these electrons go into the ring, right? We could draw a resonance structure where those electrons go into the ring, which is good or bad as far as stability goes? Good. So that makes your molecule more stable. Does that make it more or less basic then, though? If you want it to be basic and reactive, do you want it to be stable or unstable?
Unstable.
So this resonance makes this lone pair less available, right? You're saying this lone pair is in this pi system. That's going to make this lone pair less reactive, right? Because it has resonance forms within the ring, which makes it more stable. You don't want it to be stable if you want it to be basic, right? You want it to be reactive. So B is the better base because this lone pair, right? Is there any resonance that this lone pair can do? No, right? This lone pair can't move around, right? It can't be spread out. And that's what we want. We want this lone pair to not be able to be spread out because we want it to react, right? If you spread it out, you make it less reactive, right? A resonance forms make things more stable. So this lone pair, this molecule is more basic. It's a stronger base. It's a more reactive base. All right, let's take a quick look at a furan and whether or not this molecule is aromatic. All right, so the trick to this is we have to recognize, right, normally, if we had an oxygen like this, what hybrid state would that oxygen be in right there? sp3, because it wants to get all the electron density as far away from each other as possible, right? 109.5, the biggest bond angle. But once you put it in a ring and give it an option
Now it wants yes.
to have a lone pair part of a pi system, what hybridization state is it going to be? sp2, right? So that tells you being part of a pi system is really worth it, right? That's a really good thing, especially if that pi system is aromatic. So in this case, it's sp2 hybridized. And what's that going to mean about it? It has two lone pairs. So one lone pair is going to be in this, say this lone pair is going to be in what molecular orbital?
SP2.
This one can be in an sp2. And then now that means this one has to be in what molecular orbital? P orbital. Right? So it's going to be completely a part of this pi system. Now this has a p orbital, p orbital, p orbital, p orbital, right? So is it an uninterrupted pi system? Yes. How many pairs of p orbital electrons are there? 1, 2, 3. That's odd. So that makes this molecule aromatic. All right? It makes it aromatic, which is going to make it really, really stable. Right? Not very reactive. Yes. Let's do a quick reminder about acidities. So as you go across the periodic table, we have carbon, nitrogen, oxygen, and fluorine. So for all intents and purposes, we would guess, right, as electronegativity increases, right, fluorine is more electronegative than oxygen, which is more electronegative than nitrogen, which is more electronegative than carbon. So we would guess HF would be more acidic than HO, which would be more acidic than HN, which would be more acidic than HC, right? Just based on, right, electronegativity, right? So that's true. Now it becomes a little more complicated when we start changing other things, right? When we create another factor. So another factor we can involve, especially with carbon, and these other ones too, but mostly carbon, is hybridization state. Right? Carbon can have 3 different hybridization states, sp3, sp2, and sp. Those hybridization states will affect the acidity of that carbon CH bond. Right? So alkane carbon, an sp3 hybridized carbon, not very acidic at all. Actually, it's probably the worst, right? Absolutely the worst. Because, right, the negative charge would go into an sp3 orbital, right? And that's a long ways from the nucleus, which of course has a positive charge with protons. The other option we could do, what about an sp2 hybridized carbon, right? What about, right, that's sp3. What about sp2 hybridized? Well, that's not much better. We're getting a little fatter, but still really bad, right? Really high pK, not a very good acid. Where it switches, in which this is of course is very important for chapter 8, because this is the reason why we can make carbon. The one way we know how to make carbon-carbon bonds is because with an sp hybridized carbon, right? sp hybridized. Now we got that fat orbital. We put electrons in that. Now that's closer to the nucleus, that sp hybrid orbital, and that makes it more stable. So we can deprotonate this. So this actually becomes a better acid, a more reactive acid than even an NH. So this kind of hybridization kind of cheats the game here, and it ends up kind of sticking itself right in here. Right? But before we were just thinking about electronegativity, now we're looking at just hybridization. So it's hard to meld those two worlds. But this is really important, right? This is the factor we take into account. So we can actually deprotonate this to make carbon-carbon bonds, right? Make a carbon with a negative charge, and then we can make carbon-carbon bonds. Right? We still need a strong base to do this, right? Anybody else notice that? The kind of base we need is OH minus enough to deprotonate this? No. We need NH2 minus. We need a nitrogen with a minus charge, or we need butyl lithium, a carbon with a negative charge, right? This is still not very acidic, right? But it's much more acidic than these two goofballs. These guys are out in no man's land. So for this one, they're saying, in a sapling question, they're saying you're starting with, the final product is this aldehyde. And they're saying, one step back, you had step 1 was a BH3, step 2 was H2O2. And they want to know what were the 2 intermediates going backwards. So, number of carbons, 1, 2, 3, I'm not going to worry about the ring. What is one step back? What did this come from? The enol. The pi, that means the pi bond is where? Carbon 1 and 2, and there'd be an OH here, right? That H is still there, right? And then now one step back from this would be what? If I number my carbons, 1, 2, 3, what will one step back from that be? The alkyne. And where would the alkyne be between which 2 carbons? So 1 and 2. Just gotta be careful with our bond angles. 2, 3, and that's the final product they want. Working backwards, right? You kind of find, right, where the functional group's at. You kind of have to know that's where the alkyne, the other functional group's going to be at the beginning too. All right, we're going to take a look at the mechanism for this. So we're going to start with our pi bond, 1, 2, and 3. I'm going to redraw the boron, just to make it easier for myself, with its empty p orbital, right? Because boron's sp2 hybridized because it only has 6 electrons around it, right? Because it's in the 3rd period. So what happens? The boron always adds in the less substituted carbon because it's big. So this pi bond attacks, and at the same time, a BH attacks carbon 2. And that, of course, is a syn addition. All right. One, 2, 3. The next step, the OH minus just replaces the boron. Still in the syn spot, so nothing really changed, just what was where. And then of course this now is a enol, which can tautomerize to reform an aldehyde. Right? And you've seen that before, right? If I numbered these again, 1, 2, 3, and if I redrew, if I drew this pi bond, taking that H, the electrons going there between the oxygen and carbon 1. What's that going to give us? That's that taut. Right, and there, this H ends up right there or right here. You get to the aldehyde, and that's the more stable form, not the enol. Usually the ketone or aldehyde's the more stable form, not the enol. All right, taking a look at, this is number 9 from 2014 exam. So we gotta work backwards, this retrosynthetic problem. So the first thing we want to do is number our carbons. So let's go 1, 2, 3, 4, 5, 6. So working backwards, it's probably pretty obvious. Hopefully everybody sees which 2 carbons are going to be in the starting material here. 2 and 3, right? Because that's where all the stuff ends up, right? So you assume that's what those are. Another thing we should ask ourselves: how many do we add carbons? So here we start with 2 carbons. Do we add carbons? Yep. So we're going to add how many carbons? 4. Add 4 C's. And we only know one way to add carbons, and that's from a terminal alkyne. So that's probably going to be one of the first steps going forward we're going to do is add carbons, and one of the last steps going backward is add carbons. Now we start looking at so let's look at the relationships between these things. So we have a bromine and H, carbons, chlorine, a bromine, and carbons. Notice these bromines are trans to each other, and this H and this Cl are trans to each other. So what do you want to add first? So you probably know what's one step back. What is the starting material one step back? It's going to be a alkene. An alkene between which, and the pi bonds between which 2 carbons? 2 and 3. Good. Now we could probably guess, right? We know the carbons are there, right? Because we don't add the carbons till, right, the very last part of the retrosynthesis and the first part of the forward. So we'll put our numbers in. 1, 2, 3, 4, 5, 6. Now we have a tough decision to make, though. From an alkene, if you want to be sure you get a trans product, right? What do you need to put on? So what should be on it right now? So we have a choice. Do you want to add the bromines at the same time? Bromines first, or the HCl first? There's one that works better. Has to be the bromine last. You have to add the bromine last, I guess. Sorry. Because if we want the bromines to be trans, right, they have to come in last. So the difference here, so this would have to be Br, Br. So this would have to have Cl and an H. Now there's a reason why. If this was bromine and this was bromine and I try to add HCl, what would I form? What would I form? You'd form a carbocation. If I form a carbocation, am I going to have one, right? Notice this is only one. Do I say plus an enantiomer here? No. So if I form a carbocation, this all gets screwed up. So I have to put the bromines on last. That was like the high level part of this question.
So, like, you don't have the chlorine on the more, like, substituted, because, like,
Is
at
it
this
di-
point,
is
you
it-
don't have it, right? You
2 and
just,
3 are equally substituted.
right, and, like, when you're going this way, because you haven't technically, like, done the carbon part yet.
Yep. So they're equally substituted. Yep. So there's no preference there. So now one step back from this would be what? The alkyne? 6. So this reagent would be, going forward, would be HCl, right? Because remember when HCl reacts with an alkyne, what do you form? You form that the pi complex, right? That pi complex, which assures a trans addition, right? One more step back. Which bond do you want to break first? 3 or 4 or 1 or 2? 3 and 4. So we'll say we'll break that. Doesn't matter. Then we can go here. So going forward, we need step 1. We need what? A strong base. NaNH2. And then step 2, we need what? Methylbromine. Because that would be carbon 1 right there. Going forward this way, we need a strong base. Let's do, this time we'll use the ambuolithium. And what do we need? Isopropyl bromide. 4, 5, 6. And then the other ones are all you're done.
You can switch those around.
You could have switched these around. Yeah, these two order doesn't matter. So just like you could use either base, doesn't matter. But these two you wouldn't want to switch around.
You have to, like, you couldn't use NaNH2.
You can use NaNH2 twice if you want to.
Oh.
Yeah, I just wanted to show people that you obviously still use that.
So can you explain one more time why the bromine has to go first?
Because if you did the Br2 here, you would definitely get bromines trans, right? For sure. But then if I did HCl on an alkene, I would form a carbocation here, wouldn't I? Right? And once I form a carbocation, am I going to have a preference, top or bottom, wedge or hatched? No. So that's why I have to do the HCl first and the bromine Br2 second. So another retrosynthesis problem. So taking a look at this is from sapling, and one of the hard parts about this was actually they say it's trans 2 pentene, so you gotta be able to draw it 1, 2, 3, 4, 5 trans, right? So highest ranking things are opposite each other. 2 pentene, 2 carbon 2, and then it starts with acetylene. So acetylene is just a 2 carbon alkyne. That's acetylene. And they wanted you to know how do you make this. So taking first number of carbons 1, 2, 3, 4, 5. In our star material, which carbons are in our star material? Which numbers? 2 and 3. I agree. One step back. What would this have been? So it's a trans alkene. What do you make trans alkenes from? That's the reagent. What's the star material? What star material did this come from? This, not a terminal alkyne. Where would the alkyne be between which 2 carbons? 2 and 3, right? And once you get to the alkyne stage, now you can add the carbons, right? Because we should have recognized where we didn't say it, but did we add carbons here? Yes, we did. So now we have to add carbons. So we can go backwards. Let's break the other side this time. 2, 3, 4, 5. Go back one more step. So we broke here that time. Let's break here this time. And that gets us to our star material, right? So what reagents do we need going forward here? We need a strong base, so that's going to be NaNH2. Na. And how many carbons are we adding in this step? Ethyl, so ethyl bromide. So that would add carbons 5 and 4, right? 3 to 4. Again, in this step, NaNH2 is fine, strong base. How many carbons we add in here? 1 methyl bromide. So that would be carbon 1 there. Now in this step, what do we need? What reagents? Is it NaNH2? No, don't confuse yourself here. This is where people screw up. They confuse NaNH2 with Na dot in NH3. All right, notice these are different. Na dot is different than NaNH2. Right? Na dot, the lithium doesn't have a plus charge, and it's an NH3. This is that sea of electrons where you get that trans addition. NaNH2 is a strong base, where it's Na plus NH2 minus. Right, so don't confuse those two. This is the way to get trans alkenes. Right, you could also do lithium dot. Right, and that's that radical process, the fish hooks. Right.
If the H's were cis, it could just be H2
If the-
Lindlar's.
Yep, if the H's were cis, then it would be H2 and Lindlar's calculus. Right, because that would give us a cis alkane.